Hi everyone, I'm Vanto. In today's session, we'll dive deep into one of the most important data structures, the linked list. We'll explore what it is, its types, how it works internally, operations, implementation, and much more. So, let's get started. What exactly is a linked list? A linked list is a dynamic linear data structure consisting of objects called nodes, which are stored randomly in memory and connected together through links or pointers. Here, dynamic means its size can grow or shrink during execution, unlike static arrays. Linear means the data is organized sequentially. Each node contains two fields, data stored at the location and pointer to the next node in the memory. The first node has a reference pointer called head node. The last node is called the tail node and it points to null, indicating the end of the linked list. Unlike arrays, where memory is fixed and continuous, a linked list uses dynamic memory allocation. It can grow or shrink easily at runtime. To better understand this, let's use a real-world example, a train and its compartments. Imagine a train. Each compartment is like a node, and the couplings between compartments are like links or pointers. The engine is the head, it points to the first compartment. You can move from one compartment to the next in sequence, just like traversing a linked list. The key feature here is flexibility. You can easily add or remove compartments from the middle of the train without having to move the entire train or rearrange all the other compartments, just like adding or deleting nodes in a linked list. We primarily classify linked lists into three main types. The first type is the singly linked list. This is the simplest form. The linked list in which every node consists of two fields, data and pointer to the next node. The last node's pointer is null because there's no next node. It can traverse in one direction and that is forward direction. Backward movement is not possible here. Next, we have the doubly linked list. This is an upgrade of single linked list. A doubly linked list contains three fields, data and two pointers. One pointer is pointing to the previous node in the linked list and the other pointer points to the next node in the linked list. It supports the traversal in both directions. This means we can traverse the list both forward and backward. The first node's corresponding previous pointer points to null and the last node's next pointer points to null. Then comes the circular linked list. Here, the last node points back to the first node, forming a circle. The traversal will continue endlessly until we break the loop. It comes in two forms. Circular singly linked list uses the singly linked structure but connects the last node to the head. Circular doubly linked list uses the doubly linked structure but connects the last node to the head, and the head's prev pointer to the last node. Now let's see how we represent a node in code. For a singly linked list or circular singly linked list, we define a class called node. It has an int data field to hold the value, and a node next reference, which is the pointer to the next node. The constructor initializes the data and sets the next pointer to null initially. For a doubly linked list, it's slightly extended. We use a class like doubly node. It also has the int data field. The key difference is the two pointers, doubly node next and doubly node prev. The constructor initializes both next and prev to null. So, every node stores data and the reference links for navigation. Let's go through some key features of linked lists. Efficient insertion and deletion. Adding or removing nodes doesn't require shifting elements like arrays. Dynamic memory allocation. Memory is allocated one by one for individual elements as they are created. This is a major advantage for flexible memory use. Sequential access. Accessing elements is sequential. This means finding the nth element requires traversing from the beginning, which is slower than in an array. Memory efficiency. The linked list is often considered more space efficient compared to arrays when it comes to memory usage, especially for dynamic sizing, although each node has the overhead of storing a pointer. These properties make linked lists suitable for flexible data storage. A linked list supports several important operations. Insertion. At the beginning. At a specific position. At the end. Deletion. From the beginning. From a specific position. From the end. Display, to print the list. Search, to find an element. length, to count the total number of nodes. Let's walk through an example. Step 1. Create a list. Let's create a list with elements 10, 20, and 30. Now, the list looks like this. Step 2. Insert at beginning. 5 is inserted at the beginning. Step 3. Insert at specific position. 15 is inserted at position 3. Step 4. Insert at end. 40 is inserted at the end. Step 5. Delete from beginning. 5 is deleted from the beginning. Step 6. Delete from specific position. At position 3, 20 is present. Now, the 20 is deleted from the list. Step 7. Delete from end. 40 is deleted from the end. After all these operations, the list contains 10, 15, and 30. And the total length is 3. Now let's understand the algorithm step by step. Singly linked list. Step 1. Start. Step 2. Initialize the list by setting the head pointer to null. Step 3. To create a linked list. Input the number of nodes n, and for each element, input the element and call the insert at end operation to build the list sequentially. Step 4. To insert at beginning. Create a new node with the given element. Set new node next to the current head. Set the head to the new node. Step 5. To insert at specific position. Create a new node with the given element. Traverse the list to find the node right before the target position P. Adjust links. Set new node next to the current node and previous next to new node. Step 6. To insert at end. Create a new node with the given element. If the list is empty, set head is equal to new node. Otherwise, traverse until the last node, the one whose next is null. Set last next to new node. Step 7. To delete from beginning. If the list is not empty, simply move the head pointer to the next node, head is equal to head next. The old first node is automatically deleted by the garbage collector. Step 8. To delete from specific position. Handle position 1 as a special case. If position is equal to 1, then delete first node. Otherwise, traverse to the position, finding the previous and current nodes. Bypass the current node by previous next is equal to current next. Step 9. To delete from end. If there's only one node, set head is equal to null. Otherwise, traverse until the second last node. Set second last next to null. Step 10. To display list. Start from the head. In a loop, as long as the current node is not null. Print the node's data and move to the next node by node is equal to node next. Step 11. To search an element. Initialize position is equal to 1. Traverse the list, maintaining a position counter until the element is found or the end is reached. If the element is found, display the position. If the traversal reaches the end without finding it, display element not found. Step 12. To find length of list. Initialize a count to 0. Traverse the list and increment the count for each node encountered. Finally, display the total count. Step 13. Stop. This process outlines how every operation works internally. Now the Java code shows how the algorithm is translated into an actual program. I have already covered the node class. The singly linked list class contains all the methods we just discussed. Create list, insert begin, insert specific, insert end, delete begin, delete specific, delete end, display, search, and length. The main method implements a user-friendly menu using a do-while loop and a switch statement to allow the user to interact with the linked list. The options available mirror the operations we discussed. Create, insert, at 3 places, delete, from 3 places, display, search, and length. This structure demonstrates how to practically use the implemented linked list functions. We also include checks for an empty list or invalid positions to ensure robustness. Alright, let's run our singly linked list implementation and see how each operation works step by step. This command runs our Java program. As soon as the program runs, we can see the message. Singly linked list implementation. Then, we get the list of all available operations, from creating a list to exiting the program. Now, I'll select one to create a list. The program asks, enter the number of nodes. I'll enter 3, meaning I want to create 3 nodes. Then, one by one, it asks for elements. I'll enter 10, 20, and 30. So, our linked list is now created as 10, 20, 30. Here, each element is stored inside a node, and each node points to the next one, while the last node points to null. Next, I'll choose 2 to insert at begin. The program asks, enter the element. I'll enter 5. This means a new node with value 5 will be created and linked before the current head. Now, the list becomes 5, 10, 20, 30. Internally, the new node's next pointer is assigned to the previous head node, and the head reference is updated to this new node. Now, I'll choose 3, which is insert at specific position. It asks for the position, I'll enter 3. Then it asks for the element, I'll enter 15. The program traverses the list until it reaches the second node, then inserts the new node in position 3. The updated list looks like this. The link of the second node now points to 15, and 15's link points to the old third node, maintaining the chain. Next, I'll select 4 to insert at end. I'll enter the element 40. The program traverses to the last node and attaches the new node there. So, our list now becomes. The new last node's pointer is null, showing the end of the list. Now, I'll select 5, which deletes from the beginning. What will happen here is that the head will move to the next node. So the first node, 5, is removed. The program outputs, 5 is deleted. And now our list becomes 10, 15, 20, 30, 40. Next, I'll choose 6, which deletes from a specific position. I'll enter the position 3. The program deletes the element at that position, and it prints, 20 is deleted. So the list now becomes 10, 15, 30, 40. The node before 20 now directly links to the node after 20, maintaining the connection. Now, let's choose 7, delete from end. The program outputs, 40 is deleted. Here, you should notice that the last node's pointer is updated to null. So our list now becomes 10, 15, 30. Now I'll select 8 to display the list. The program prints 10, 15, 30. So these are the current elements of the linked list, displayed in the sequence they are linked. Next, I'll select 9 to search for an element. I'll enter 30. It traverses each node and finds the element at position 3. So it prints, element is found at position 3. This shows how searching is done sequentially. The program checks every node one by one until it finds the target value. Now I'll choose 10 to find the length of the linked list. The program prints, length of linked list is 3. That's because currently our list has 3 nodes with elements 10, 15, and 30. Finally, I'll select 11 to exit the program. The message appears, exiting the program. And that ends our linked list execution successfully. Linked lists are chosen in specific scenarios due to their characteristics. They are ideal when the amount of data is constantly changing. They are useful when you need dynamic memory allocation during runtime, as they only use memory needed for each node. They excel when the program requires frequent insertions or deletions because these operations are highly efficient. When you want efficient memory usage, they offer efficient memory use by allocating space only for actual elements. They are suitable when the order of traversal matters, but you don't need random access to elements. Some real applications include. They are the underlying structure for implementing stack, queue, and other data structures. They play a role in dynamic memory allocation in operating systems and compilers. Used in core tasks like memory management, process scheduling, and file systems. The list of zones is linked, allowing you to easily go to the previous or next track. The browser history or the function of the previous and next page buttons is often managed by a doubly linked list. Despite their benefits, linked lists have some drawbacks. Slow access time because elements can only be accessed sequentially. You must traverse from the head to find an element. They require higher memory use because every node must store the data plus one or more pointers, increasing the overhead compared to just storing data in an array. The use of pointers or references can make them complex, difficult to debug, and harder to maintain. Since the memory is non-contiguous, they are generally cache inefficient. Time complexities. Insertion and deletion are very fast in the best case, being order 1. This is achieved when operating at the head. In the worst case, to find the insertion or deletion point, you might have to traverse the entire list, making it order n. Traversal always requires visiting every node, so it's order n, in both best and worst cases. Search is best case order 1, if the element is the first one, but worst case order n, if the element is last or not present. Some common exceptions in Java when working with linked lists are: null pointer exception. Occurs if you try to access data or the next pointer of a node that is null. Example: if the linked list is empty and you try to delete an element or display the list, it can trigger a null pointer exception. Index out of bounds exception. Occurs when trying to access or delete an element at an invalid position in the list, like if the position is beyond the bounds of the list. Example: if the list has only 3 elements, but the user tries to insert or delete an element at position 5. That's all about linked lists. You can also check the description for the PDF version of these notes. Thanks for watching.